Welcome. Today, we are diving deep, really, really deep, into the fundamental building blocks of our entire universe. We're talking about the atoms that make up literally everything you can see, feel, and even are.
I mean, it's a huge question, right? When humans have been asking for thousands of years. Think about the chair you're sitting on, the air you're breathing, the stars in the night sky. What on earth connects all of those things? Well, the answer is both incredibly simple and profoundly deep. Atoms. Everything is made from these ridiculously tiny particles. But, just calling them tiny particles kind of sells them short. It doesn't really get to the heart of just how fundamental they are.
So here's a great way to think about it. Picture a single Lego brick. An atom is just like that. It's the absolute smallest piece you can have that still has the properties of the whole thing. It's the smallest possible unit of blue 2x4 Lego brick. If you break that brick down anymore, you just have plastic dust. It's not a Lego anymore. So, keeping that Lego idea in our heads, let's get a little more specific and pin down what these universal building blocks truly are. Here it is, the official definition. An atom is the smallest unit of an element, like gold, oxygen, or carbon, that you can possibly have. If you have one single atom of gold, it still is gold. It behaves like gold. But if you were to split that atom, well, you don't have gold anymore. And that right there is the crucial point.
All right, so we've established that the atom is the basic unit. But what's going on inside one? Let's zoom way, way in and meet the little inhabitants that give each atom its unique personality. So there are three main players in this subatomic world. You've got the proton, which has a positive charge. Then there's the neutron, which is, well, neutral, no charge at all. And finally, you have the electron, a tiny negatively charged particle that's just buzzing with energy. And this table here lays out the key differences perfectly. Protons and neutrons are the heavyweights. They both have a mass of about 1 atomic mass unit. That's just the scale we use for stuff this small. They live together right in the center, while the incredibly lightweight electrons exist in the space outside of that.
And that center has a special name, the nucleus. This is where all the positive charge from the protons and almost all of the atom's mass is concentrated into an incredibly dense, tight little ball. Okay, get ready for this, because this fact is just wild. Even though the nucleus contains pretty much all the mass, the atom itself is over 99.9% empty space. Seriously, it's like having a marble in the middle of a giant football stadium. So then, why doesn't your hand just pass right through your desk? Well, it's because the electron clouds of the atoms repel each other with an incredibly powerful force. What you feel as solid is actually that force pushing back, not solid matter touching solid matter. Mind-blowing, right? So what about all that vast, empty space? Well, that's ruled by the electrons, and they aren't just flying around randomly. No, they follow a very specific, and honestly, a very strange set of rules. You can almost think of it as a kind of cosmic address system. The first and most famous rule is Heisenberg's uncertainty principle. What it says is that on this tiny quantum level, you simply cannot know an electron's exact position and its exact momentum, where it's going and how fast, at the same time. The very act of perfectly measuring one totally scrambles the other. So what does that mean in simple terms? It means we have to completely give up on the idea of knowing an electron's exact location. The best we can ever do is identify its general neighborhood, the area where it's most likely to be found. And that probable neighborhood has a scientific name, an orbital. Now, this is not a fixed path like a planet orbiting the sun. It's more like a cloud of probability, a 3D region of space where that electron spends most of its time. And there are specific rules for how electrons settle into these orbital homes. First, they always fill the lowest energy spots available, kind of like water filling a container from the bottom up. Second, no two electrons in an atom can have the exact same quantum address, or set of properties. And third, electrons prefer to have an orbital all to themselves before they're forced to pair up with another one. But how in the world did we figure all this stuff out? Our modern understanding of the atom is the result of a centuries-long scientific detective story, with each clue building on the last one. It started with Dalton just imagining a simple, solid ball. Then Thomson discovered the electron and pictured his plum pudding model. After that, Rutherford's famous gold foil experiment revealed the tiny, dense nucleus and all that empty space. Then Bohr came along with his mini solar system model, which was a huge step forward, before we finally arrived at today's wonderfully weird quantum model. So the really crucial point here is this massive shift in thinking. We went from Bohr's neat, predictable little solar system where you could know an electron's exact path to the modern quantum model, which fully embraces uncertainty and just gives us a map of probabilities. It's way less intuitive, but it's far, far more accurate.
Okay, this is all fascinating theory, but why does it matter to you? How does this abstract world of orbitals and probability connect to your everyday life, like, say, the phone in your hand?
It all comes down to the electrons in the outermost shell. These are called the valence electrons, and they are the frontline soldiers of chemistry. Their desire to be shared or stolen or given away dictates how atoms bond together to form, well, everything. Understanding these rules unlocks, well, pretty much everything. It explains all of chemistry, why the periodic table is shaped the way it is, and even how we can know what distant stars are made of. It's the absolute foundation for nuclear energy and for the semiconductors that power all our modern electronics.
And that really brings us to the ultimate takeaway. Atomic structure isn't just some abstract topic in a science textbook, it's the fundamental grammar, the underlying language that matter itself uses to write the story of the entire universe. And the question is, now that we're learning to speak that language, what are we going to build with it next?